Okay, Ahmed, I have shared my screen. Are you able to see it?
Yes.
All right. Okay, perfect. So, right. So I'll give you a quick recap of what we have discussed so far, and then just we'll continue with the top contents. Right. So the very first thing which we discussed in the last class was different sets, like natural numbers. Instead of natural numbers, we have all the positive integers. We don't have zero. We don't have negative integers, and we only have whole numbers. In whole numbers, we had zero as well, and rest of the set was just like the set of natural numbers. In integers, we have both positive negative integers and zero as well. Okay, then in positive integers we only have positive integers. In negative integers we just have negative integers, and we do not have zero in positive and negative integers. Okay, so just be clear with this. If I talk about odd numbers, we have odd numbers only, and in even numbers, we have even numbers only, and zero is an even number. Okay, so just know that. Right. Then, if we talk about prime numbers, we have all the prime numbers in this set. Okay, then these things were easy, but then when we discussed rational and irrational, so in this part, I told you that any number which can be written as a fraction, like p by q, where p and q belong to integers, is a rational number, right? If I talk about this definition, this is q and this is q dash. Okay, this is q complement and this is q. And we read this set this way, that q set has all the x's such that every x is written as p by q, where p and q belong to integers, right? So in this set, we are going to have numbers like 2 by 3, like 4 by 6, like 1 by 2, right? Fractions. So any number which can be written as a fraction is a rational number, and numbers which cannot be written as a fraction are irrational numbers, right? And if we talk about real numbers in general, in maths, every number is either a rational number or an irrational number. So are you clear so far?
Yes.
All right. Then we talked about this. Rest part was like easy. Rest of the things were easy. But this was the important part, irrational and rational numbers. In irrational numbers, we said we are going to have non-terminating. Like this is the example of non-terminating when we are going on continuously till end. And in non-recurring, again, it is um, non-terminating and the numbers after the decimal are not repeated, right? Like in this case, in the recurring one, if I talk about this, we have it is again non-terminating, like it is not stopping. We have 1 3 1 3 1 3 1 3 and so on, but still the numbers are same, so we can write this way. So in irrational numbers we have non-terminating and non-recurring, right? Are you clear with this? And this is also important. Whenever you have a surd,
Yes.
such a thing is called surd, right? When this part is not a perfect square and like you have under root 3 or under root 7, something of this sort, this is an irrational number, because in NEP, in those MCQs, you will get to see such questions quite a lot. Okay, so just know that under root 2, under root 3, and such numbers are irrational numbers. And if we talk about rational numbers, we have terminating decimal like 0.78 or like 0.65 or 0.025. All these are terminating decimals. Or even if we have non-terminating, but it should be recurring. Now here 4 to 4 is being repeated. 4 to 4 is being repeated. So this is the recurring type and this is the terminating type, right? So are you clear with these things?
Yes.
Okay, perfect. All right, then we discussed two operations. One was unary, in which we said that an operation which converts one number into another, just like under root or trigonometry or derivatives, right? Any operation which makes this number into another number, right? Any operation which converts a number into another one, right? So this was easy, and we are not supposed to discuss this too much because this is something which we know, but this is the new thing, binary operation, right? And we have to discuss this again. An operation which converts two numbers into third, a rule denoted by static in a set S that assigns to any pair of elements of S taken in a definite order to another element of S. Okay, so I'll tell you in simple words. Binary operation has a set. This set could be a set of natural numbers, real numbers, positive integers, right? We have discussed many sets. So it could be any set, and then we have a binary operation. This could be plus, minus, multiplication, division, right? And yes, we have other ways of defining these operations as well, but so far and at this stage, just know that we have these four operations, right? Okay. And then the final thing is that this is a rule denoted by static. For this, we take two elements from set S, let's say A and B from set S, and this is how we denote it. And we get a third element, and this third element should also belong to S. So are you clear with the definition of binary operation? That two elements from a set, we have to apply the operation, and we want the third element to be part of set S as well.
Yes, good.
Okay, so this is the basic definition. But in order to make a simple operation into a binary one, or in other words, the difference in a simple operation and a binary operation is this, that whenever we have a binary operation, it should satisfy six properties: the closure law, the associative law, identity law, inverse property, commutative law, distributive law, right? And in the last class, we discussed closure law. So closure law says whenever we have two numbers, x, y, belonging to our set, in this case, you're talking about real numbers, and their operation is plus, okay? So the third element which we get after applying the operation, that is x plus y, that should also belong to the set of real numbers. So this is the closure law, and this is what we said in the definition as well, that this element right here, which we get after applying the operation, should also belong to set S. In our example, S is real numbers and the static is plus, okay? Because here we're discussing particular examples, okay? Right. And again, if we talk about binary operation as multiplication, so we have two elements x, y, which belong to our set, that is of real numbers, and x, y belongs to R. Okay, so this is how the closure law is satisfied, that the third element which we get after applying the operation between two numbers should also be in the set, right? So are you clear with this closure law?
That's good.
Okay. Then we discussed associative law. This is very simple. We just said that we need to have x plus y plus z and x plus y plus z equal. Then the associative law operation would be satisfied. And in case of multiplication, same was the case, but the operation was multiplication. This is something which you would already be familiar with. Like this is what we have been doing. We know that addition and multiplication satisfy the associative law, right? Okay. Then this thing was different for you, identity law. Let me just okay. Now can you still see the screen, the new tab?
Yes.
Okay. So over here, basically, we have discussed closure law, associative law, and now I am on the identity law. So right, so let's read it again, okay? Because this is what we have to discuss. Like we already discussed this in last class, but still it is important. It is new as well. Identity law. Right.
Yeah, remember, an identity law
All
is
right.
0 for
Yes, very
addition
excellent,
and 1
excellent.
for multiplication.
Very well done, very well done. And you know that this zero should belong to your set, whatever it is. In this case, it is a set of real numbers, and this one should belong to your set again. Okay, then the identity law for addition and multiplication will be satisfied. Very well. Excellent. Okay. And do you remember inverse property as well?
Yes, but one more question. You said this 0 should belong to the set of real numbers. So
Yes.
what are the situations where 0 doesn't belong to
Okay. Okay. For
the set
the
of real numbers?
identity law, right? For the identity law.
Yeah.
Okay. Now, obviously, we know that the set of real numbers, they have 0 in it, right? So, okay. So these are real numbers. Okay. This is the set of real numbers. Real numbers have both rational and irrational numbers. So they do have 0 as well. Like if I can explain you this way, that in the set of real numbers, we have, all right, so let me just write it down here. So let's say this is R. And if I talk about this set, we have all the negative numbers which we have in maths, minus 7.86, minus 7, minus 6.5. We have, so many numbers. Then we have 0, like we have every decimal, fraction, whole, positive, negative, or even every number in maths which you have studied so far is a real number. Okay, so we have 0 in the set of real numbers. We have 0 in the set of real numbers. But if I talk about another set, let's say I talk about set of natural numbers, right? If I talk about set of natural numbers, in the set of natural numbers, we do not have 0. The set is starting from 1, 2, 3, right? So if I say, if I say that, my set is of natural numbers, which basically starts from 1, 2, 3, so on. And other than the set, the operation here is addition. Now let's try applying it. Now obviously it would be closed, because if I take two numbers from the set of natural numbers, let's say I have 2 and I have 3, and apply the operation, the third number which I am going to get would certainly be in my set of natural numbers, right? Because I have every positive integer in set of natural numbers. So whenever I will add two positive integers, I will certainly get a positive integer. So this would be satisfied. Again, associative property.
But this is closure law.
Yeah, this is closure law. This is closure law. Yes.
Mm.
This is closure law, which is satisfied for natural numbers. Associative law would also be satisfied, right? You know this because addition and multiplication is always has always associative property, right? So this would also be clear.
Okay.
But if we talk about the identity law, now here we want this. We want this. We want that 0 should belong to the set of natural numbers, which is not the case. We do not have 0 here. So this means that identity law cannot be satisfied with respect to addition in case of natural numbers, right?
Yes.
Identity law cannot be satisfied. With respect to, you have to write it down. Obviously, you won't be writing it down in any T. You have to choose from your answers. But yes, you should be clear with respect to this because questions would be of this type. Okay, that it could be that we will see questions now as well. But still, the question could be identity law in the set of natural numbers. In natural numbers cannot be satisfied with respect to addition. Let's say we have two options, addition, and B is multiplication. Now, if we talk about multiplication, right? Let's say this. Know that this is multiplication. If we talk about multiplication, for multiplication, we want 1. We want that 1 should belong to natural numbers, and it certainly does. We have 1 in natural numbers. So yes, if we talk about multiplication, the identity law is satisfied with respect to multiplication. So the answer would be A in this case, right? Because identity law cannot be satisfied with respect to addition because we do not have 0 in n, but we do have 1. So multiplication, when we talk about with respect to multiplication, the identity law is satisfied because we have 1. So very well said. You are 100% correct. Just know You don't have to learn any definitions or stuff like that for MCQs, okay? You should just know that if you have 0 in your set, it means that the identity law would be satisfied with respect to addition, because 0 is the identity with respect to addition and 1 is the identity with respect to multiplication, right? So is this thing clear?
Yes.
Very good. Okay. So if we talk about, if we discuss inverse property quickly, here I will tell you that we need, for all x's belonging to the set, in this case we're talking about real numbers, there should be a minus x such that x plus minus x is equal to minus x plus x is 0, right? Don't get confused by this part, because in addition and multiplication, we know that addition and multiplication is commutative. That basically means that a plus b equals to b plus a. Okay, so this is what they are trying to say, and there would be questions in future, which like if you do your bachelor's in maths or so, that you will see that we don't only have plus and multiplication as operation, but we have other operations as well. Okay, so such things are they are important in those operations. Here we're talking about addition and multiplication, so we know that they are already commutative. Okay, so the reason behind writing this and then this again is just to tell you that they should satisfy the commutative property as well, but at your level you should not focus on that. Just know that for inverse property we need such a number in the set for every number, that if I have a in my set, I should have a minus a such that I get 0, right? This is for addition. And if I talk about multiplication, so in this case, if I have a, I should have 1 by a such that I get my multiplicative identity, that is 1, right? So this is what you should know. Now I'll give you a quick example. If we talk about set of integers, in integers we have negative integers, we have 0, we have positive integers, right? Now, obviously, in this case, if I say that a is 2, I do have minus 2. I do have that multiplicative inverse, which when I will add to my element, I will get 0. But if I talk about set of natural numbers, let's say, in this example right here, if I talk about set of natural numbers, I do not have negative integers, right? So I would not be having the inverses of 2, 1, 3. I don't have minus 1, minus 2, minus 3, because only then when I add minus 1 to 1, I will get 0, right? So are you clear with this thing?
Yes.
So obviously, if I talk about set of integers, and yes, with practice, you will understand 100% that which set is satisfying everything and which set is not. Okay, so far we are doing it in a mixed way. So if I talk about set of integers and we're talking about the inverses, we do have the additive inverses. Okay, additive inverse of any number in case of addition is the minus version of that number, right? If 2 is the number, minus 2 would be its additive inverse. If minus 2 is the number, 2 would be its additive inverse, right? Then if I talk about 10,
Multiplication.
yeah, minus 10 would be its additive inverse. Okay, so we are clear with this part, right? Let's talk about
Yes.
multiplication. If we talk about multiplicative inverses, let's say my element is 2, my multiplicative inverse would be 1 by 2, because only then I will get 1, right? So
Mhm.
if a is the element, 1 by a would be its multiplicative inverse, and if 1 by 2 is the element, 2 would be its multiplicative inverse, okay? Right, Emmet?
Understood.
Okay. Now, if I give you a quick recap, here when we were talking about the set of natural numbers, we said that we do not have the additive identity with respect to addition. Set of natural numbers, and we did not have the 0, but we have 1. So identity law with respect to multiplication was satisfied in case of set of natural numbers. But if we talk about the inverse property, do you think that the inverse property would be satisfied with respect to multiplication? No, because let's say if my element is 2 I do not have 1 by 2 instead of natural numbers, right? I do not have 1 by 2. I only have whole numbers. So multiplicative
Hmm.
inverses are not there in the set of natural numbers. So this means that although things were clear
Right.
till the identity law, the inverse property is not satisfied, right? So what does this imply? That multiplication is not a binary operation in the set of natural numbers. Are you clear with this?
Yes, except for one.
Yeah, exactly,
No.
exactly. But
Hmm.
look, here we have for all x's belonging to the set, which means that for every element of natural numbers, we need to have this to satisfy the inverse property, right? This is okay if we have the inverse of 1, that is 1 by 1. But since we do not have the inverses, the multiplicative inverses of other elements in n, this property cannot be satisfied because these are the wordings. This is for all. This means for all x's belonging to the set of, let's say, natural numbers, we need that 1 by x should also belong to the set of natural numbers. Okay, so for all, it is okay if we have for 1, but for in order to satisfy the inverse property, we need it for all elements, okay, and not for one only, right, Ahmed?
Yes.
Are you sure that this is clear?
Yes.
Okay, very good. Okay,
Okay,
finally,
give me 2 minutes. I'm coming.
yeah, sure.
Yes.
Okay, right. So far we have discussed 4 laws which were important for an operation to be a binary operation: closure law, associative law, inverse law, and identity law, right? And now we only have 2 left, which are very, very simple. One is the commutative law. I told you already that this is the commutative law. So if
Hmm.
we have A plus B and both these A and B belong to this is basically defined in terms of like for the set of real numbers and for addition, right? If I talk about the
Right.
commutative law in general, I'll tell you. So in general, we have for all elements AB belonging to the set S, X binary operation Y should be equal to Y binary operation X, right? This is what we have
Right.
when we talk about the commutative law. So if I talk about this example particularly, here we have set of real numbers. Here, sorry, this should have been A and B and A, right? Okay. So here, since our elements are X and Y, they are saying X binary operation plus Y equals Y plus X, right? So this thing is clear. And if we talk about multiplication, so in that case, again, we have A static B, B static A. The only difference is here we have static equals dot, that is multiplication. So X dot Y equals Y dot X, right? By changing the order of elements, the answer should not change. This is what the commutative law says. So are you clear with this?
Yes.
Very
Yes.
good, very well done. Okay. And finally, we have the distributive law. So the distributive law says distributivity of multiplication over addition is how they write it. So this law basically is that if you have x, y plus z, this should be equal to xy plus xz, right? And like we know this already, if we multiply x with y, we get xy. When we multiply x with z, we get xz, right? But in this case, whenever you will be proving this, you won't be doing it this way. You will do this side, you will do this side, and you have to show that both these sides are equal, right?
Right.
Right? Okay. And then again, this is same if we have x plus y into z. This is xz plus yz, right? This is the distributive law, and this is actually true because this is what we have been doing. And you know, the operations like in plus and multiplication, in for these operations, all these laws are going to hold. This is why we have particularly discussed about addition and multiplication, right? So are you clear with these laws, all of these?
Yes.
All right, okay. All right, so we are done with all everything except complex numbers. Let's just do that. All right, okay, perfect. So I will stop sharing my screen and I'll share the whiteboard.